All right, well, hey, welcome to February, if you can believe it. We're already a month down in this class, which means we're a third of the way. Holy cow, we're flying. Yeah, that's how quarters roll. So today's plan, of course, we're going to go ahead and start with homework questions. After that, we're going to talk about yet another distribution, the one called the normal distribution, and this is the biggie. This is the one that everything's kind of built off of. So we'll look at the normal distribution and talk a little bit more about it. And then we'll spend some time talking about the exam that's coming up on Thursday. So things to expect, what you need to know, that sort of thing. So that's my plan for today. But before we get into that, let's start with homework. So I know that Allie shared one that she wants to look at from uniform distribution. So we'll go and look at that. But other things that people want to look at? Things that
Can we go over probability distribution tables? Because I don't really necessarily understand how to solve them.
Okay, so probability distribution tables. Do you know what section that was? Is it called probability?
Chapter 4, discrete probability and the binomial distribution.
Okay, we'll see if we can find that one.
Okay,
sure.
I think it would be nice to go over question 3.
Okay.
Just for like reference.
We can definitely do that. Okay, and so Willie, you're saying you're having trouble with standard deviation, uniform distribution. Okay, I'm going to guess that the question that Allie wants to look at, because it had like lots of multiple parts, probably also includes that, but we'll make sure that we've got that down. Okay. Anything else? And as always, if things pop up, you can throw it into the chat or just speak up and we can go and look at those. Okay, so let me go ahead and share my screen and we'll go check out some of these homework problems. So let's start with the discrete probability and binomial distribution. And it was number 3 in that, was that correct?
Yeah.
Okay. Okay, so it says, suppose that you are offered the following deal. You roll a 6-sided die, so just a standard die. If you roll a 6, you win 20 bucks. If you roll a 4 or a 5, you win $5. Otherwise, you pay $2. Okay, so we're just going to be, doing a little gambling here, this made-up game. But basically, you roll the die, the outcome tells you what happens. You either win 20 bucks, win $5, or you owe $2. All right, so it says complete the PDF table. List the X values, where X is the profit from smallest to largest. Okay, so let's just think about profit. Like in this case, what are the 3 different amounts that you can win?
Um, 25 and 2.
Okay, so we can win 20, we can win 5, but we can't actually win 2. We'd lose 2, which means we're going to win -2. I know it's kind of a weird thing to think about, but if we're going to talk about our profit, which is how much we gain, when we lose, we actually gain a negative. So in terms of the 3 values that we can actually get here, they're going to be -2, 5, and 20. All right, so this is the first thing that's a little bit tricky when you have something like this one, is that sometimes we don't think about results as being negative, but this can definitely be negative. I can be out $2 really easily, right? I roll a 1, 2, or a 3, and I lose $2. All right, so that's actually a negative result for me. The other ones are positive though, right? I mean, in fact, quite positive. I like getting 20 bucks when I roll the 6. All All right, so those are going to be the x's. So anytime you have a probability distribution table, what you want over there with the x's are your possible outcomes. And in this case, the possible outcomes are we're down $2, we're up $5, or we're up $20. All right, so now what we need are the probabilities of each of those. Like, what's the likelihood that we're going to owe $2, or that we're going to win $5, or we're going to win $20? So let's start with the losing. No, let's start with the winning 20 bucks. Let's be positive, right? So what's the probability that we win 20 bucks? I roll that die, and what's the likelihood that I get a result that makes me win 20 bucks? So let's think probabilities again. Remember, they're fractions. The bottom of the fraction are all the possible outcomes. And the top of the fraction is the outcomes that we're interested in. So let's think about this. To get $20, what has to show up for me to get $20? Right? It's got to be a 6. So we're going to end up getting a probability of 1/6. Oh, I should have been paying attention to the chat box. You guys are all nailing it. Okay, good. So yeah, so it's going to be 1/6. But it does say round to decimal places where appropriate. To 4 decimal places. Well, I'm going to go ahead and say 0.1667. Right? If it's 1 out of 6 is 0.166666666, but rounded to the fourth decimal spot is 0.1667. All right, so there's our probability there. All right, so what about the probability of getting $5? All right, so I have a bunch of people throwing this in. It's going to be 2 out of 6. All right, thanks, Bruno, for reducing that fraction. So it's going to be 2 out of 6 or 1 out of 3. Okay, so 1/3 of the time, we're going to win $5. Cool. All right, so as a decimal, that's going to be 0.3333. And then lastly, to end up losing $2, that's going to happen if we roll anything else, and the other possibilities are 1, 2, and 3. So that's a 3 out of 6 chance, or 0.5. So half the time, we're going to end up owing $2. A third of the time, on average, right? Remember, probabilities are on average. A third of the time, we're going to win $5, and 1/6 of the time, we're going to win $20. All right, so our 3 outcomes and their 3 probabilities. Okay, so now let's find the expected profit. So this is the expected value. So do you guys remember how to find expected value? Remember what we do? So I see Bruno frantically typing something in, so maybe he's giving me the answer. Or maybe he's just looking up to see who's winning the basketball games tonight. All right, so, okay, so we multiply the probability times the outcome value. So let me go to whiteboard here and show you how this is going to play out. If we want our expected value for this one, we think about the 3 different results. There was the -2, and we're going to multiply that by its probability, which was half the time. And then we're going to add to that, well, our next possibility was $5, and that happens 1/3 of the time. And then the last possible outcome was $20, and that occurs 1/6 of the time. All right, so again, what we got going on here is just result times probability. Okay, so if we think about what our different results are times our probabilities, and then we just add them up. All right, so this is going to be -1 plus 5/3 plus 10/3 if we reduce that. So that's -1 plus 15/3, which is a nice number, luckily for us. And so the expected value here is 4. So what this means is that if you played this game lots of times, just many times, on average, you're going to win $4. Now, never on any single roll will you win exactly $4, right? Sometimes you win 5, sometimes you use 20, sometimes you lose 2. But if you were to do this lots and lots of times, over the long haul, you would average a $4 victory every time. Okay, so let's go back to the question and see what we need to do here. Okay, so the expected profit, rounded to the nearest cent. I don't need to round to pennies. I know it's exactly $4. Okay, so let's interpret that. So let's see. You will win this much if you play a game. Is that true? That if you play a game, you're going to win $4? And that's a pretty easy no, right? You're not going to win $4 ever. Okay, so it says if you play many games, you will likely win on average very close to $4 per game. Or this is the most likely amount of money you will win. Well, that's false for sure, right? Because again, you can't win $4. So it turns out for this one, it is if you play many games, you'll win on average $4, right? The first one, you will win this much if you play a game. We don't know how much you're going to win if you play a game. That's an unknown. Every time I take a die and I roll it, I'm unsure what the outcome is. That's part of what makes these games fun, right? Is that, ooh, am I going to win this time? The last one here where it says this is the most likely amount of money you will win, that is also false. What's the most likely amount? In this question, what's the most likely amount? Yeah, thanks, Willie. It's -2, right? That's got the highest probability. So the most likely thing to happen is that you lose $2. But over the long haul, you're going to win around $4 a game. Okay, so based on the expected value, should you play this game? What do you guys think? Yes or no? Would this be a game worth playing? I know my answer. All right, so Bruno just said yes. What do the rest of you guys think? Well, I'd say Ali, you say no. Yeah, Bruno, you got to win big. Hey, as they say, go big or go home, right? All right, so I'll tell you my answer. My answer is I play this game every opportunity. Every opportunity you give me, I'm going to play this game because I want to play this a lot. Because if I play this a lot, I know on average I'm going to be plus $4. So if I play this 100 times, I'm going to be up around $400. Will I be up exactly 400? Probably not. Probably not. But it'll be close to that. Like I would be surprised if I played this 100 times and I was only up $200. I'd be shocked. Right? I would be flabbergasted if I was down money after playing 100 games. Now, playing 5 games, I could easily be under. easily, because that's not very many. Because remember how probabilities work. These are long-term expectations. The expected value is what happens after lots of results. So I'm going to go ahead and put yes, but let's see why. So yes, because you can win 20, which is greater than what you lose. No, that's not it, because it could be that I lose more often, so that'd be a problem. No, this is a gambling game and it's always a bad idea to gamble. All right, well that's not a mathematical judgment, right? That's more of a morality judgment. Yes, since the expected value is positive, you'd be very likely to come home with more money if you played many games. That is definitely my answer. Right? But if you look at this one, it says no, since the expected value is negative, you'd be very likely to come home with less money. And that is the case. If this was a negative number, that's when I would say, nope, I'm not doing it. All right. Do you guys remember the game show Deal or No Deal? The one where they had to open up the cases and they had monetary
Yes.
numbers, right?
Yes.
And then the banker would always be like, okay, I will let you, I'll give you $125,000 if you trade in your case. So to me, as a mathematician, whenever I would watch that game, I'm not a huge fan of it because like, it's just all luck and they draw it out. So, but me as a math guy, I always would look at that, what they're offering, and I would compare it to the expected value. And I always told my wife, if I was ever on that show, I would make it very clear that if the number they offered me was under the expected value, I would not take it. Because I'm a nerd like that. But it's that same kind of idea. However, in that case, you're not playing that game lots of times. You're only playing that game one time. And so the expected value doesn't really pay out. But anyway, if expected value is negative, don't do it. And for those of you that are in Tahoe, we've got on the Nevada side, we've got all the casinos. I will just tell you that all of the games in the casino are set so that there is a negative expected value. It might be a very low negative expected value, like when they talk about slot machines that have like a really high payout, or as they like to call them, they call them loose machines. Those things will have like, for every dollar bet, the expected value is like -3 cents, right? So your return is 97 cents on every dollar you bet, which isn't bad, right? I mean, you're only losing 3 pennies every dollar you play. And so for you, that feels pretty good, right? If you were to put in $100, in the end, you're going to be returning home with 97 kind of idea, right? So it's not like you don't really notice it, but to the casinos, that's huge. If they get 3 cents on every dollar, think about how many millions of dollars are put into slot machines. Those pennies definitely add up. Anyway, so I forget who was this. Ashton who asked about this one. Are you feeling a little bit better about this?
Yeah. Thank you.
Okay, you're welcome. I'm going to go ahead and get some points while I'm here because my grade is really lacking. You'll notice I only have 3 out of 18 on this homework set. Okay, so I think that was the only one that came up from this section. So let me go over to the uniform distribution and we'll see if we can hit both the standard deviation and then some of those other pieces that Allie was curious about. So was that just the regular uniform distribution section? Probably, since that's got way more questions. Let's go check it out. And Allie, I'm going to turn this to you. Was there a specific number you wanted to look at?
All of them, but we can go over number 1, I guess.
All right.
And number 3, apparently.
And no, I just randomly picked one. I don't really care. They're all pretty similar, huh? Okay, let's go ahead and let's see. This one's got a few more. So let's go to number 2 here. So it says, suppose that the weight of a newborn fawn is uniformly distributed between 1.7 and 3.4 kilograms. All right, so before we go further, what does uniformly distributed mean? And I asked this question mostly as a to stress that it's important to know what distribution you've got. So what does that mean if it's normal? Okay, so all outcomes are equally likely. Thanks, Willie. So if we look at this one, actually, you know what? Since number 3 came up multiple, we'll go look at number 3. But again, so it says, today the waves are crashing on the beach every 5.4 seconds. Times when a person arrives at the shoreline until crashing is observed follows a uniform distribution of 0 to 5.4 seconds. Okay, so this means that it's just as likely to see a wave crash 1 second after you get there, 2.6 seconds after you get there, 3.9 seconds, like any value between 0 and 5.4 is just as likely. All right, now it's going to be super important later, like when we get to after we've talked about so many distributions and they all apply differently, it's going to be super important to be able to recognize what the distribution is. And in fact, that's the number one thing you should always do. I mean, that's what you should concentrate on in any one of these problems, is looking at it and figuring out what kind of distribution. Because as soon as you know what kind of distribution, you know how to find all the other things. Okay, so this one's uniform. Now I'm going to go ahead and write this information down because we're going to need to go to the whiteboard, I think, to try some of these or do some of this stuff. So let me see here. We got 0 to 5.4 seconds. And some things that we're going to be looking for are the mean, the standard deviation, the probability that X is exactly 0.7, the probability that we're between 1.8 and 2.3, the probability that it's going to take longer than 3.78. Let's see, so then part F. Suppose a person has already been standing on the shoreline for 1.3 seconds. Find the probability that will take between 2.6 and 3.8. Okay, and then 71% of the time, a person will wait at least how long before the wave crashes in. And then we want to find the minimum for the upper quartile. Whew. All right. So there's a lot of stuff we need to find out about this, but it all comes back to the fact that it's uniform distribution. So let's draw our pictures here. Let me go back to the whiteboard. I'm going to go ahead and just clear this real quick. Okay, so here's what we know. It's uniform. And we're between 0 and 5.4. So if you remember the notation that we used the U to say that it's a uniform distribution, and we have to put the regions on it, 0 and 5.4. So I want to draw a graph of this thing. So here's 0, somewhere out here is 5.4. And if it's a uniform distribution, it looks like that. Everything is just as likely, so our probability density function is a line. It's a horizontal line. It does something like that. Now, before we calculate anything in terms of like mean and standard deviation to answer all the questions, I want to figure out, what is this probability right here? What is that probability? What is that that's equally likely? So do you remember how we find that? How we find that amount? All right, good, Willie, thank you. It's going to be 1 divided by B minus A. Because remember, the area in any kind of a distribution is always equal to 1. So we know the area of this rectangle equals 1. So 5.4 times its height is going to equal 1. So the height is 1 divided by 5.4. All right, so let me just go ahead and take out my trusty calculator here and get that real quick. And so that is around 0.185. It's actually 0.185, and so on. But we'll go ahead and just leave it like this. Okay, so this is actually the probability, 0.185. All right, now let's start calculating everything that we need to find. All right, so for part A, it said we want to find the mean. So do you remember how to find the mean? It's actually really easy for uniform distribution. So Ali says here, add the first and last and divide by 2. Yep, that's exactly it. We want the halfway point here, because the mean is always at the halfway point with a uniform distribution. And so that's the average. So it's 0 plus 5.4 divided by 2, which is 2.7. Okay, so 2.7 is the mean. It's also the median. I don't know if you guys can see that. The 2.7 is the median because 50% of the distribution is above it and 50% is below it. So uniform distribution is cool there because the mean and the median are exactly the same number. All right, so there was part A. So now part B, we want to get the standard deviation. All right, so how do we calculate the standard deviation for a normal distribution? Or sorry, not a uniform distribution. All right, this one's not as easy. There is a formula for it, though. It's the square root of b minus a squared divided by 12. All right, so where that comes from, I'm just going to tell you the math says it must be, right? You can actually, you can prove it, but we're just going to go with this is the formula for it. So we're going to put in our values. So b minus a, that's 5.4 minus 0. So we're going to get 5.4 squared divided by 12, all inside that square root. All right, so let me see what that gives me. I get 1.5588. We'll take it to 4 decimal places just for the heck of it. All right, so basically all you need to do is figure out what is the length of your interval, square it, divide by 12, and then take the square root. All right, it's just that's the formula for it. All right, so we've got our mean, we got our standard deviation. Now, when I was first asked about these by Ali, she was like, oh, I understand the first couple parts. It's the later parts that are problems. So I'm going to guess that like up to this point, we're probably doing okay because it's just plug into formulas. So let's see what happens when we move to the next pieces. Okay, so the next one says, what is the probability that x is exactly 0.7? Okay, so what's the likelihood that you have to wait exactly 0.7 seconds before you see a wave crash on the beach? All right, so what's the answer to this one? Yeah, it's 0. You gotta love this. I don't know if you remember me mentioning this, but when you have a continuous distribution, the probability of any one specific value is actually 0. All right. It's just any one specific value is 0. So this one, because it said exactly 0.7, is going to be 0. It doesn't matter what that number is. Could have been anything. Could have been pi. Could have been 5.2216843. It could have even been 1. Doesn't matter. Okay, so that one, that might feel a little cheap, but probability of any one specific value is actually 0. Okay, so let's look at what the next one said. The next one said, what's the probability that you have to wait between 1.8 and 2.3 seconds? So I'm going to go ahead and write this with the probability notation. But this was the next one. All right, so what we're going to do here, we're actually going to come back to this graph. And let's put on here 1.8. So there's 1.8 and say 2.3. So those are the two numbers that we're curious about. So the probability, what I'm looking for here with my probability, is going to be the area of this right here. Because the probability of an interval is the area under the curve in that interval. All right, well, for uniform, these are nice because they're rectangles. And rectangles, we know how to get their areas. Their width times their height. So their width, the width of this thing, let me actually write here is width times height. The width is going to be 2.3 minus 1.8 because those are our values here. The height, well, that was that 1 over 5.4. I'm going to not round it right now. I'm going to leave it as 1 over 5.4 just because I don't want to have a rounding error that's perpetuated. All right, so I'm a big fan of waiting to the end to round, but we'll go with this. Okay, so 2.3 minus 1.8 is 0.5. So we get 0.5 divided by 5.4. And that gives me 0.0926 if we go to the 4th decimal place. All right, so the way to interpret this is that 9% of the time, roughly 9% of the time, you have to wait between 1.8 and 2.3 seconds to see that wave crash on the beach. So when it comes to these probabilities, it's all about area. It's all about area. And for uniform, that just means areas of rectangles. And we're going to see that play out with this next one. So the next one, this was part E, I guess, if I'm keeping track properly. It said, what's the probability that you have to wait at least 3.78 seconds? All right, so it's going to be a probability that x is greater than 3.78. Well, we can do the same thing somewhere in here. Is 3.78. If we're going to be waiting more than that, that's in here. And so I need to know the area of this rectangle. Well, again, it's going to be width times height. Its width is going to be 5.4 minus 3.78 because those are the bounds on this interval. And the height, again, is that 1 over 5.4. All right, well, let's see what my calculator has to say about this one. All right, so this time I get 0.3 exactly. Okay, so the way to interpret this is that you have to wait more than 3.78 seconds 30% of the time. So almost a third of the time, you're going to have to wait at least 3.78 seconds to see the wave crash on the beach. But I want you to notice how similar D and E were. They were very similar questions, at least in terms of how we answered it. I mean, it may have felt completely different. One, we were looking for the probability of being between some values, and the other is what's the probability of having to wait more than. But in terms of how we built it, yeah, area of a rectangle. All right, so there was part E. All right, but now part F. This is the one that's a little bit interesting. I want to go back so you can see the wording on this. Okay, so let's go look at part F. So it says, suppose that the person has already been standing at the shoreline for 1.3 seconds without a wave crashing. Find the probability that will take between 2.6 and 3.8 seconds for the wave to crash into the shoreline. Ooh, okay. So this is a conditional probability. What about this tells me that it's a conditional probability? And I'm really asking that question to, you know, kind of get you to start thinking about it. All right, so Ali, you said it's the and. Yeah, it's the fact, like Willie just said there, that you've been standing there for 1.3 seconds. So that's a given. We already know that nothing's happened the first 1.3 seconds. So because we already have some information, this thing is conditional. Okay, so let me go back to the whiteboard and I'm going to write it with the probability notation. So we want to figure out what's the probability that the wave crashes somewhere between 2.6 and 3.8 seconds, given that we're already greater than 1.3 seconds. So remember that vertical line, right? That vertical line right here is just saying that's a given the next thing has already happened. So we already know that we've been standing on the shore watching for 1.3 seconds. So now the question is, what's the chance that it's going to happen somewhere in here? All right, so for the conditional probabilities, this is how these guys work out. Let me see if I can erase some of this stuff without destroying the major parts. Yes. Okay, so let me start with where we're looking, right? We're looking between 2.6 and 3.8. So we want to know this right here, right? But this isn't out of the entire thing. We're already restricted, right? We were told that x is greater than 1.3. So really the question is, what portion of this blue is the green? So we need to take its area and divide the green area and divide by the blue area. All right, now I told you that there was a faster way when we were doing uniform, and that's just looking at the interval lengths. But let me just kind of build it. If I look at the area of the green, it's got its width 3.8 minus 2.6 times the height, 1 over 5.4. The blue restricted, it's got its width, 5.4 minus 1.3, also times its height, which is the 1 over 5.4. But since it's uniform, you'll notice that these guys cancel. And so all we really need to do is just take a difference of the endpoints in the interval to get the length of the interval. So this one's 1.2. The other one is 4.1. And we can just divide those guys. So let me do that real quick. And I get 0.29227. Again, we'll round to the 4th decimal place. It's 0.29268. So again, this is right around 30%. So if you've already been waiting for 1.3 seconds, there's a 30% chance that you'll actually see the wave crash between 2.6 and 3.8. All right, so that's conditional. So when it's conditional, think about the area from the condition, and you're going to divide that into the area of what you're interested in. All right, I've completely forgotten what the next question is. My notes don't really help me here. So let's go back and read what it says. And there's a lot to this one, right? Okay, so G, 71% of the time, a person will wait at least how long before the wave crashes in? All right, if we want to put this into stats terms, this is asking us to figure out a percentile. We're trying to find the 71st percentile. All right, now that probably helped absolutely nobody. So let's come back to this picture and talk about the 71st percentile. So let me get rid of all this conditional stuff. Now, if we're going to do a percentile, what we're looking for is a place here where, in this case, 71% of the area is to the left of it. Right, percentile, that's what percentiles mean. That means that that value is bigger than 71% of the rest of the data. So 71% of the time has to be below that. So basically what we're trying to figure out is what is the area, or what is that time value that's going to give us an area of 0.71. All right, so it's an unknown amount, right? Call this guy X. But I know that X times the height is going to have to equal 0.71. Again, this is width times height. I'm leaving it here not to round again. All right, well, to solve that, I just need to multiply by 5.4. So I get 0.71 times 5.4. Multiply those two guys together. And I get 3.834. Okay, so if you wait 3.834, there's a 71% chance that you saw the wave crash down on the beach. But I actually have a feeling I screwed this up. I want to go back and look at what it says again. The wording is super important. 71% of the time, a person will wait at least how long before the wave crashes in? All right. Let me show you. 71% of the time, you have to wait this long. Yeah, I answered this question incorrectly. All right. So why am I wrong here? Can anybody see why I did this wrong? And it has nothing to do with the idea of doing the area or my calculation. How did I misread this? Does anybody see it?
Shouldn't we be using percentiles for this one?
Well, that is what I did. I did use a percentile. Maybe I didn't interpret it wrong. Yeah, you know what we're going to do? We're going to plug that number in. We're going to see if that works. Anybody remember what that number was? 3.834. We'll see here. But for sure, we can answer part H. So find the minimum for the upper quartile. So for the upper quartile, what percentile is that?
Would that be 75%?
That would be 75. So basically that picture we just did, if you were to change that to 75, that's going to give us the quartile. So 0.75 times 5.4 is 4.05. So that's going to be Q3. Right? That's the lower bound of the upper quartile. All right, so let me go back and let's just check this real quick. I'm going to go ahead and see if I get that point as well. Yep, okay, I did think I misinterpreted this. So you notice that for G, I got the red X of shame, right? And so the reason is this. So if it's 71% of the time, a person will wait at least how long? What I did was 71% of the time, a person will wait at most how long? So let's go back and look at that G again. And I see that Willie caught that put that in the chat, the at least. Let me erase some stuff here. Get rid of a bunch of garbage. Okay, so let me come back to this one. So it said I wanted to know at least how long. So instead of my picture with the 71% the way I had it before, what I need is 71% to be more than that, right? Because at least means you're the smaller side. You're the smaller amount of time. So I actually need it to be set up like this. Okay, so it turns out that we're going to use a similar idea. I still need to use this area idea, but now my width is actually, 5.4 minus x. If I want to know the different, the distance between these, I take 5.4 minus my x. So I need that 5.4 minus x times 1 over 5.4, that was its height. I need that to equal 0.71. So let's just adjust this a little bit. So I'll multiply by 5.4, that gives me 3.834. Now I need to solve for my x. So we'll subtract 5.4. Right, I'm just moving stuff around. So that leaves me a negative 1.566. And then I just have to change the signs on those. Divide by -1. Give me x equals 1.566. All right, so I did that. I made that mistake on purpose. Yeah, I'm bullshitting you. I didn't make that on purpose. But take from this a serious lesson, right? That the wording is extremely important. You change just a slight different wording and you get a completely different answer. So be really careful when you read it. I definitely read that one a little bit too quickly, but the actual value we need to have there is 1.566. But notice that all of this probability stuff, whether it's actually calculating the probabilities or finding percentiles, all comes back to areas. And that's always the case with these continuous probability density functions. But with uniform, the areas are always rectangles. We like rectangles. Rectangles are easy. The area is base times height, right? Ask Bruno sometime if you want to talk about finding areas of really hard things, because that's what we're doing in calc. He's in my calc class as well, right? But if you have weird shapes, you got to use calculus, and then it gets cumbersome. Rectangles are super easy. Man, Bruno would kill for rectangles on his calc test on Friday. I'll tell you what. All right, so are we feeling better about this? I hope. Hearing nothing, seeing nothing, I'm going to assume is yeah, we feel a little bit better. But for all of those problems, whether we're talking about, in that case, waves crashing on the beach, or we're talking about weights of newborn fawns or whatever, if it's uniformly distributed, you're still going to want to do the same thing every time. So draw the pictures. Think about the rectangles, length times width, right? Base times height. That's how you're going to find and answer all of these things. So if it's find the probability, you already have the numbers, you multiply them together. If it's a percentile, you're basically given the probability, and then you have to end up dividing by the height to get your interval width. All right, well, Allie, I will take your somewhat better as an answer. I'm always happy with that. Okay, so there's some good review about uniform distributions, and that stuff is going to be on the exam that's coming up on Thursday. So it's good that you get in there and practice that, and it's good that you asked that question so we could talk about it a bit. All right, so what we need to do for the rest of today, we need to move on, and I want to show you this next distribution because it's the granddaddy of them all, as they say. All right, so let me go ahead and hop up to my whiteboard. So I'm just going to leave you here for 1 second, and I'll be right back. All right, so we'll go ahead and get it out of the way. Here's your Star Wars shirt of the day. This one you got to think about a little bit. Unless it's Yoda. OOYL. Just think about it. All right, instead of YOLO, think about how Yoda would say, you only live once. Only once you live. It's like, yeah. All right, well, anyway, there's your Star Wars shirt of the day. Okay, so today's distribution is the biggie. And this one's what we call the normal distribution function. Now, the normal distribution is defined by two things. You may remember that all the distributions have something that defines them, like the uniform. We had to know where we started and where we ended. The binomial, I know that one wasn't a continuous, but the binomial, we needed to know how many trials we were doing and what the probability of success was, right? So all distributions have things you need to know. But for the normal distribution, you need to know two things. You need the mean of the population and you also need to have the population standard deviation. So those are the two things that have to be known in order to use a normal distribution. So the way we're going to write this, x is our variable. We're coming from a normal distribution, so capital N. And then in here, we're going to have a mu. And we're going to have a sigma. Okay, so you need to know your mean and your standard deviation. All right, now I'm going to write up the formula for the PDF, the normal PDF. Do not memorize this. Don't even try to memorize it. We're never going to use it. I just want to show you how much more complicated it is than some of the other ones that we've seen, right? With the uniform, it was whatever the number was. F of x was equal to this number. The exponential, you may remember we had e to the minus 1 over mx, right? And so we had those kinds of forms. This one is gnarly. This one is totally gnarly. So do not try to memorize this. We've got f of x. It's equal to 1 over sigma times the square root of 2 pi times e to the negative x minus mu quantity squared divided by 2 sigma squared. I told you it was ugly. Again, don't try to memorize this. Please don't. Please don't. All right. But I just want you to notice that it does have an exponential piece to it, just like we saw before. But this one's a little bit funky because it's got this negative power. But because of the squares, negative powers on exponents, I don't know if you remember this, but you take e to a negative power, it decreases as you go far away. But this thing is such, because we're squaring these numbers, that it decreases as you go far away in each direction. And so the shape that you get, and this is important, so now you want to watch this, but the shape that we see for a normal distribution is one that looks like this. All right, so here are axes. All right, we're going to have probability up here. This is going to be where we happen to be. This is going to look like this. So the graph of a normal distribution has this shape right here. It's the one that's called a bell curve. So if you've ever heard that term, the bell curve, that's what this is. the mean is exactly in the middle. Okay, so it's the high point. It's the place where we have greatest probability. That would be when x is equal to mu. If x is equal to mu, this is all 0. E to the 0 is equal to 1. And so the greatest probability is 1 over sigma times the square root of 2 pi. So notice that the height of this depends on sigma. It depends on the standard deviation. It depends on the spread. Okay. All right, so let's talk about what happens to this graph when you fiddle with sigma and you fiddle with mu and all that good stuff. Okay, well, if sigma increases, so increasing the standard deviation, it flattens the bell. So remember, standard deviation is just telling you how much the data is spread out. So if the data gets spread out a lot, if there are lots of values that are far away from the mean, it's going to cause this thing to shrink. It's going to flatten down. And you can see that in the formula. If sigma gets bigger, if you divide by a larger number, you get something smaller, right? Like think about this. If you divide by 100 compared to dividing by 2, you get a much smaller number. So you can see that there, but you can also reason it out by thinking about what probability is. Probability is the total area under the curve, right? Well, if we spread this out, we're making it so that there's more further away, we're gonna have to shrink it if the total area has to equal 1. Okay, so that's what's gonna happen if we change sigma. The bigger sigma is, the flatter this curve, the less bell-shaped it happens to look. If sigma gets small, so things are not spread out very much, that bell gets nice and tall and kind of gets a nice big peak. All right, so that's what happens with sigma. If you change mu, so if we change the mean, but we keep the standard deviation the same, changing mu only moves the graph left and right. So that means it doesn't really change the distribution. It just changes the values, right? So like if we have two normal distributions where the means are off by, let's say 1, that just means that we took that graph and we shifted it 1 over. Everything is still the same, basically. We just changed the intervals. We increased them by 1. All right. Now, one thing that is important, where like this equation isn't super important, I want to remind you about the empirical rule, because we can apply the empirical rule to this. I don't know if you remember the empirical rule, but the empirical rule talked about how much of the data we should expect within certain distance from the mean. So let me just remind you about that. To use the empirical rule, you had to have data that was, or a distribution that was symmetric. You can see that this is definitely symmetric. There's a mirror image. And it has to have like, one peak in the middle, which this does have. So the empirical rule applies. And so just remember that this means that there's 68% of the data is within 1 standard deviation of the mean. So if we were to go out one standard deviation, okay, so let's just say that this is a standard deviation. That means that the area in here is 0.68. So just like when we were talking about the uniform distributions and finding probabilities, it's the area under the curve. Well, the area under this curve between 1 sigma below the mean and 1 sigma above the mean is going to be 68%, so 0.68. If we go to 2 standard deviations, this was 95%. All right, so on the graph, let's say we go out another standard deviation. So now if you look at that total area, is going to be 0.95. So 95% of the data is between 2 standard deviations above and 2 standard deviations below the mean. And then if you go a third standard deviation, it's an insanely large amount. It's almost all of the data. It's 99.7%. And you can see that on the graph as well, right? If I add in one more standard deviation, let's say that brings us out to here. All right, so we've gone 3 standard deviations. Now we're up to 0.997. And you can see that there's just an ever so slightly small amount of stuff that's still out here. There's a little bit of area. There's a little bit of area, but there's not much. All right, so standard deviations play a huge role here in terms of getting us probabilities. And obviously, if that's something that we're curious about, and we are a lot, right? We try to figure out what's going on. We can use those standard deviations as our guide. We basically just need to know how many standard deviations away are we. So quiz for class. And this is good for our review. Do you remember something that we saw before that tells us the number of standard deviations away we are? You remember what that was called? Good, thanks, Carolina. It's the z-score. So one thing that we're going to be really interested in when we're talking about these normal distributions is z-score. Z-score is a big, big deal. So let me remind you about that. This is probably also worth knowing for the exam on Thursday. I'm just saying. I mean, I haven't written the exam yet, but if I were a betting man, and I am, I would bet that there's something about z-scores. Okay, so the z-score. Again, it's the number of standard deviations away. And when I say away, I mean away from the mean. And so it's actually a really easy thing to calculate. You take your data, your variable number, you subtract the mean, and then divide by the standard deviation. So we get x minus mu all divided by sigma. Okay, so remember how to find the z-score. Because here's what we can do. Since normal distributions all look alike, they all have the same shape, they all follow this rule, what we can do is, instead of worrying about any one specific, normal distribution, we can make them all the same. We can basically scale them all down using z-scores. So in essence, what you can do is you can take something that's a normal with mu and sigma, and you can convert it using z-scores into one that's normal with a mean of 0 and a standard deviation of 1. So basically, we've standardized it. We've made it so that we can compare two normal distributions directly. Like it makes it so that they're the same. It's not apples and oranges anymore, as they say, but standardizing it makes it so we can compare them. So this one's called the standard normal distribution. All right, now you don't have to use this one. You absolutely don't have to use this one, but it's a really easy one to use if you've already taken things and just determined z-score. Back in the day, before we had the technology that we have now, before you had these handheld calculators and computers and stuff like that, this was actually really important because finding probabilities using the normal distribution is very difficult. But it had been done, and it had to be done by hand, which you can just imagine how awful that must have been. No calculators and all that kind of stuff. But basically, they built a table, they built a chart for probabilities and values according to z-scores, so that then you could take whatever your normal distribution is, calculate the z-scores, and then use that table. All right. So this used to be a big deal, like a really big deal. Now, not so much, but it's still really handy. And it's a lot easier if you just start thinking about things in terms of standard deviations. Because if you were to tell me you get a z-score of 1.5, I know exactly where that is. And I also have an idea of what kind of probability that means and blah, blah, blah. All right. So, but you can always convert it. If you just look at z-scores, the normal distribution looks like this. All right. So I want to do a couple of problems with it. I want to apply this normal distribution just so you can kind of see how it works. And I also found online a TI-84 emulator. It's actually an 84 plus. So I'm going to pull that up. I'm going to share my screen so that you can actually see the commands and what you need to do. All right. And we can even later, we'll look at how you can use it for things like the binomial and other stuff that's going to be on the exam. If you have a different kind of TI, it's going to be similar. So if you got an 83 or an 84, it's going to be very similar steps you need to do. But this way, at least I'm able to show you since I don't actually have a TI-84. Anyway, so let's start with this example. Well, maybe even before I do that, let's talk about some of the places where you get normal distribution. The normal distribution happens all over the place. That's why it gets its name, normal, because it's like one of the usual ones that you see. But places you'll see it, let's say we're going to talk about average height of adult humans, right? And if you want to even get more specific, let's say we could say adult males or something like that, so that we don't have to worry about the fact that genders have different heights. Well, let's say we're going to look at average height or heights of, adult males. Okay, we all have different heights. All adult males are going to have different heights. But if you were to go out to the entire population on Earth, look at all of the men, measure their heights, you would end up seeing a graph that looks like a normal distribution. There are some really, really tall people. They're on the very far low end. There are also some very, very short people. They're on this side on the low end. but most people are all around the same height, right? Like think about men, what average height I think is like 5'10", maybe at least in the US, that's the number I'm thinking. So our mean is 5'10". So you take someone like me, I'm a little bit taller, right? I'm a little over 6 foot, but I'm not crazy tall. It's not like I'm in the NBA. So I would be on the hump, but before it gets really low. Similarly, I've got a brother who's 5'7". All right, he's again a little bit on the shorter side, but not crazy short, right? And so that'd be an example of where you get normal distribution. Most characteristics of animals in terms of body, like body size and weights and stuff like that, they tend to be normally distributed. It's pretty interesting. So here's another example of where that would be, is if you look at how much blood is in a body. All right. So on average, an adult human has 5.2 liters of blood. All right. So your body may not have exactly 5.2 liters. In fact, the probability that your body has exactly 5.2 liters is 0. Right? Probability of any one specific value of none is 0. But you're going to be around there. Some of us have more, some of us have less. It's usually dependent on your body size. The bigger you are, the more blood you're going to have because you've got more cells that need to get it, and blah, 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 right? But on average, it's 5.2 liters of blood. All right, so that right there is your mean. That's the average amount. Now I'm also going to give you your standard deviation. So the standard deviation for this is 0.3. So I'm going to put here on average with a standard deviation of 0.3. So that number 0.3 is just giving you an idea of the spread. So remember that empirical rule. We know 65% of people, of adult humans, are going to have between 4.9 and 5.5 liters of blood. 99% of people, or 95% of people, are going to be within 2 standard deviations, and then 99.7 are going to be within 3. So let's just look at that real quick. So we know 65% are going to be between 5.2 plus 0.3 and 5.2 minus 0.3. That was the one standard deviation. So that's how I came up with those numbers of 4.9 and 5.5. So it's very likely that you're going to be somewhere in there. If we bump it up a notch, we know that 95% are going to be between 5.2 minus 2 times 0.3 and 5.2 plus 2 times 0.3. So 2 standard deviations. So if we put those in, that's 4.6 and 5.8. So 95% of people are going to have between 4.6 and 5.8 liters of blood in their body. All right, and then if we were to go one more standard deviation, that gets us to the 99.7. I'm not going to bother writing out the calculations. I'm just going to subtract another 0.3 and add another 0.3 from each one. And so we just accounted for almost every adult human, right? 99.7%. So that's what these numbers are doing for us. Okay, so I wanted to work through this just so you could see what standard deviation is really telling us. All right, but now let's talk about doing some probabilities here. All right, so for example, what if I wanted to know what percentage of people have more than 5 liters of blood? Okay, so this is the next question I want to answer. Is what percent of people have more than 5 liters of blood? So let me draw a picture here. Here's our normal distribution. I know that the mean was 5.2. Let me put an axis on here. All right, but I want to know what percent of people have more than 5 liters of blood. Okay, so somewhere on here is 5. So I want to know what is this area right here. All right. Well, this is where we go. I don't know calculus. I don't know how to do this. Right? You need calculus to do this. All right. However, technology is going to be your friend and is going to take care of this for you. So let me hop to my computer, and I'm going to share with you the screenshot of my TI-84 emulator, so we can talk about what commands you need to use in order to do this. All right, so hopefully everybody can see that emulator now. All right, these are actually free. I have like a 90-day free trial or something like that. Maybe it's a 30-day, I don't know. So if you need one, you can actually download this. It's actually a pretty easy thing to do. But let me show you how we're going to do this. So while I'm at it, I'm going to show you all kinds of stuff with the stats. So for what you're going to want, most of it is going to be found in in a couple of different places. One is the button that says stat. Hopefully you guys all see that guy. Right? It's right here. If you hit the stat button, you're going to get a little window, a menu. And so you notice that this one, first of all, it says edit. This is where you could actually put in a list to do some statistics. If you arrow over, it goes to calc, and here are all the different things that you can calculate. Right? One var stats, one variable statistics. That's going to give you mean, median, quartiles, things like that. A bunch of the other stuff, don't worry about just yet, but we will see them later, like linreg. That's linear regression. Let me arrow down. I think these are mostly all regressions. Yeah, so we'll see regressions when we get to, I think, chapter 12. So that'll be a while. But if you arrow over, then you see a bunch of things that say tests. These we will also see coming up. Z-test, t-test, prop Z test, all that stuff will make sense later. All right, so right now, the only thing in here that you're going to ever do are one variable statistics. You need to have a list of data. Once you have a list of data, you can actually do this. So let me just show you real quick. Let me run over here. Let's edit. I'm going to hit 1. I'm going to put in a list. Let's just put in a list of data. So I'm going to put some random old numbers in here. Okay, so I just put a whole bunch of stuff in there, list 1. Let me show you how we could actually do the one variable statistics. So I'm going to go stat. I'm going to arrow over to calc. I want one variable statistics, so I can hit 1 or enter either way. Okay, so it says, what list do I want? Well, I put it all in list 1. Then it says frequency list. Well, I don't have a frequency list. Frequency list would be like we've done before, where we put the our result and then how many times it occurred. So I don't have one. So I'm just going to hit enter, enter, and calculate. And it thinks for a minute and it spits out all this information. So X bar, that's my average, my sample mean, 21.4. Here's the sum of all my sample values, 214. SX, sigma X, remember the difference. S is your sample standard deviation, sigma is your population standard deviation. Here are my N, I did 10 of them. My smallest is 15, my first quartile is 18. I keep arrowing down. My median, 22.5, third quartile, 24, max is 27. So it's really, really handy. Put it in, get your answer. Okay, well, that's not really relevant to what we're doing right now. So let me show you where you're going to find those. If you look above theirs, in blue here, it says distr. Well, that stands for distribution. So I'm going to hit second, theirs, and this brings up my distributions. So I mentioned this last time when we were talking about like binomial and stuff like that. This is the list of all the different distributions that this calculator knows. So it knows normal PDF, normal CDF, inverse norm, inverse T, T PDF, T CDF, chi-square PDF. Okay, there's a ton of them. The ones that you're going to want to know about. Normal. That's what we're doing right now. Again, PDF, CDF, as we've talked about. PDF gets you the probability of that value. So that's the function value there. Normal, or the CDF, adds them all up. I'm going to arrow up so you can see the bottom of the list. Like here's geometric. We talked about geometric. Poisson, we talked about. Binomial, we talked about. So this is where you're going to find all those different things. So for example, let's go do a binomial PDF. Oops, overshot. I want to just show you how this works. So you hit enter. So remember, for binomial, you need to know how many trials and what the probability of success is. So that's the first thing it asks you. So binomial, let's say we're doing 50 trials. We're going to toss a coin 50 times, let's say. All right, so if I toss a coin 50 times, the probability is, no, let's roll a die. Let's roll a die. All right, and let's say we're looking at how many roll a 1. So the probability of getting a 1 is 1 in 6. So 0.16666. We'll call that good. All right, so now with binomials, remember this was the how likely are you to get a certain number? So let's say I roll a die 50 times and I want to know how likely is it that I roll 11 ones? Okay, so this is going to be the probability that out of these 50 rolls, I get exactly 11 ones. All right, well, let's just go down here and hit enter. So you'll notice that here's the command is Binomial Pdf, 50 trials, probability of success. I want to know how likely am I to get 11. I hit enter. And there you go, 0.08405. So there's an 8% chance I get exactly 11 ones. All right, so it's actually kind of nice. It walks you through what you need to do with these different guys. All right, now let's go to the one that we're specifically talking about. Enough of this. Let's go back to distributions. So we're going to be looking at a normal distribution. So do I want PDF or CDF here? If I'm going to try to figure out what percent of people have more than 5 liters of blood.
CDF?
That's going to be a CDF, right? Because I don't want a specific value. I want an interval of values. So we're going to go and do a CDF, number 2 here. All right. Now, for the TI-89, or sorry, 84, this is set up so that you can put your lower and upper bounds on here. So my lower bound was 5, right? I wanted to know how many people have more than 5 liters of blood. All right, now I need to give it an upper bound. Now for my upper bound, I want it to be as big as possible. So here's what we're going to do. We're going to do a little trick. We're going to type 1. And then if you look above this comma, there's in blue, it says EE. I'm going to go hit that button because that's my scientific notation. And then I'm going to hit 99. So this is, technically, we would say that this is a big ass number. But that's the technical term for it. It's a 1 followed by 99 zeros. Okay, so that's a huge number. So basically, we're saying we're going to go to infinity. All right, so I want 5 to as big as I can get. So anytime you're trying to go as far as possible, put in a 1E99. If you're going to do a lower, you want to go towards negative, put a -1 E99. All right, but now I need to give it my mean and my standard deviation. So you notice that this is already set with 0 and 1. The default is going to be to go to the standard with the mean of 0 and the standard deviation of 1. However, we can set it to be whatever we want. So let's do our specific values. So we had 5.2 for our mean. And our standard deviation was 0.3. All right, so I'm going to hit enter again so you can see what the command looks like. So it's normal CDF, lower bound, upper bound, mean, standard deviation. I hit enter, and I get 0.7475. So if we come back to what our original question was, what percent of people have more than 5 liters of blood? Well, there's your answer, 74.75% of them. All right, so here's how the normal CDF works. It's super easy. It's just a matter of putting in your lower bound and your upper bound, and you can standardize it or not. You just have to put in your proper mean and standard deviation. All right, so that's cool. But what about this question? I'm going to come back to the whiteboard. So that's great and all. But what if I asked you this? What if the question was 30% of the people are within how many liters of the mean? So same question. I mean, we're still talking about the blood deal where we've got 5.2 liters on average with a standard deviation of 0.3. But I want to know, okay, 30% of people are within how many liters of the mean? Now, I gave you a percentage that wasn't nice. Like if I had told you 65% of the people, you should be able to answer that question pretty easily. How close are you if you're going to be within, if we want 65% of the people? You remember what the empirical rule said? Okay, so it'd be 1 standard deviation or 0.3 liters. So we'd be between 4.9 and 5.5. Okay, but I didn't ask for 65%, I asked for 30%. All right, well, that's what this looks like on the picture. Let me draw the picture again. So, I'm going to do a new one. I'm not going to try to recycle. So we've got this right here. So here's our 5.2. And basically, I want to know how far do I go from 5.2 so that I'm catching 30%. So I want this area to be 0.3. All right, so notice that there's a little bit of a difference here. The question I asked before, I didn't know an area, but I knew my X value. This time we're kind of going backwards. Right? We're going backwards here, where I know my area, but I don't know my X value. Okay, so we're going to want to go backwards here. But what we're going to use to help us with that is what's called the inverse norm. Okay, so we were just using the normal CDF and PDFs as commands. There's also one called the inverse norm. All right, and how this works is you put in a percentile. And you get out the X. Okay, so it's going backwards. And that's why it's called inverse. You may remember from algebra, inverses. Those are functions that go the opposite direction. Okay, so inverse norm, it's give me a percentile and I'll give you an X. And this is actually really handy for things like quartiles and stuff like that. So for example, if we were to do inverse norm of 0.25, that's going to give us Q1. That's going to give us the first quartile, because it's going to tell us how far do we go so that we have 25% in here. And it's going to spit out Q1. If I wanted the third quartile, I want to be out here, I want to be at Q3. If I put in 0.75, that's going to give me Q3. If I want the median, because now this is 75% of the area. So if I want the median or the mean, I would do 0.5. So notice though, that with inverse norm, it's telling us how far we have to go from forever down here on the left to get up to this percentage. So like the question that I just asked, if I were to put in 0.3 and do inverse norm, I'm going to be very wrong with my answer. Because it's not going to find that 30%. It's going to find out how far do I have to go till I get a total of 30%. So we're going to have to be careful with this thing. But this is how inverse norm is going to work. It's going to spit back how far we have to go to get that percentage. All right, well, to answer our question, we still need to do that. We still want to use this inverse norm, but we're going to have to get creative about it. Okay? So check this out. What can you tell me about the percentile for 5.2? 5.2 is the mean. What percentile was that? Yeah, it's the 50th percentile. So what I know is that to right here, and I'm going to do this in kind of a teal color, this is an area of 0.5. Now let's see if we can be sneaky. So let's just think about this purple area that's to the right of the mean. Let's just think about that piece right there. Can you tell me how much area is in there? And before you fall for it, don't say 0.3, because it's not 0.3. Looks like we're maybe struggling a little bit to get that number. Let's think about this. I asked you to figure out how much is going to give us 30% if we're straddling the mean. But I'm only looking on one side of the mean. So I don't actually need 30% over there. How much percent do I need on either side of the mean to get a total of 30? All right, thanks, Willie, for throwing that in. It's going to be 15%. So this little bit is actually 0.15. So how much total area is there until we get up to this point? Well, we'll take that 0.5 and the 0.15 and add them together, and it's 0.65. So to get this one, we're actually going to do inverse norm of 0.65. And that's going to give me the biggest number for this region. So like I said, you got to get creative sometimes when you're doing this. And I highly recommend you draw the pictures, because it will help you spot what we're doing. These inverse norms, we're starting on the very, very far left, coming out to a specific place. So if we need to go beyond, right, or sometimes we have to subtract, sometimes we have to add, but you can get creative, and seeing those pictures can definitely help you. I promise as you work with the homeworks and you try these, you'll get more comfortable with them. This one is about as tough as they get. All right, well, let's go to the calculator and let's see if we can, and let's play around with inverse norm. So the first thing I want to show you is we're going to get the quartiles. All right. Calculator, there it is. All right, so let's go to distributions. And you'll see that the third one down here is called inverse norm. So let's go to inverse norm. So notice the first thing it asks is the area we want. So let's find the first quartile. So we're going to do an area of 0.25. Again, it defaults to the standardized 0 and 1, but let's change it to our specific guy, which was 5.2 was our mean, and 0.3 was our standard deviation. Okay, so again, if you look at this, you see inverse norm, 0.25, that's the amount we're looking for. There was our mean, our standard deviation. And so we get 4.99765. So basically the first quartile is 5. You can round that to 5. So 25% of people have less than 5 liters of blood. Now, let's say we want to do the third quartile. I'm going to show you a little trick here. You can arrow up. So you're on the inverse norm command and hit enter. And it's going to bring it back down. But what I'm going to do is I'm actually going to backtrack over here. Oh, too far. And I'm going to put a 7 there. So now it's going to calculate the third quartile. So 75% are under 5.4 liters. So you can actually expedite this a bit instead of going back through the menus every time. And that's what I'm going to do here again, because I want to change this to 0.65 to answer our question. So we'll change that to 6. Hit enter. So we get 5.31559. All right, so that's the number at which 65% of the people have less than that much blood. But for the interval that we were looking for, that's the bigger number. Okay, so that's what inverse norm does. Now I'm going to go back to the whiteboard. Let me get rid of the share. But we're going to keep track of that number. All right, so we found that that was 5.3156. We'll round it off. Okay. So the answer to our question, right? 30% of people are within how many liters of the mean? That's not this answer. We're not 5.3 liters away from the mean. This is how many liters we have to be at that point. If I want to find out how many liters from the mean we are, I have to subtract my mean. And what I get is 0.1156. So the answer to this question is 0.1156 liters. So if I take my mean and I either add or subtract 0.1156 liters, I've now caught 30% of the people. All right, so this is another one where wording is going to really matter. You have to pay a lot of attention to it to see what exact command we're going to use. But the big ones are normal CDF and inverse norm, where you put in the percent. All right, so there's a little bit more in terms of how to use the normal distribution. You don't have to standardize it, but it's definitely useful with those z-scores. All right, let's take a little break. I feel like I've been talking forever. I see we got about another half hour, so let's just take a short break. I'm going to come back at 5:30. It says 5:24 on my clock right now. I'm going to come back at 5:30. Going to share a little bit more about this, and then we'll review for the exam on Thursday. Okay, so again, you'll know I'm back when you see my image. All right, so I will see you guys in just a few minutes. All right, so let's talk a little bit about this exam that's coming up on Thursday. So things to know, things to be ready for. I'm often asked what's a good way to study for exams. One good thing to do for sure is to go back and look at quizzes that we've taken. We took a few, I think 2 or 3. So you can go back and look at those quizzes, see the kinds of questions I asked. The exam questions are going to be very similar. They're also going to be very similar to your homework. So something else you can do is go back to those homework sets and try similar problems. Even though you've already gotten grades and you can't change your scores and all that, you still can go back and you can practice. So practice similar problems is a great way to kind of review for what's going to be coming up. So what's this exam going to look like? Well, first of all, it's going to cover chapters 1 through 5. All right, so chapters 1 through 5. So that does not include what we talked about today. The normal distribution is not part of that, but chapters 1 through 5. So it's a little bit different than what the syllabus says. If you look at the syllabus, it says chapters 1 through 6. We're going a little bit slower than I had anticipated, but that's not a big deal. We're just going to make it so that the exam is chapters 1 through 5. Okay, so what's it going to look like? It's actually going to look a lot like the quizzes, just longer. It is going to be designed to be a 2-hour test, but you'll still have 2.5 hours to get it turned in and uploaded. So how many questions? I couldn't even begin to guess, Bruno. I have no idea. And it's funny, I know I always get asked that about exams, and my brain goes to, why does it matter, right? If I tell you there's 10 questions versus 15, does it change what you do? I mean, I don't know, maybe it does, but I don't know because I haven't written it yet, so I have no idea what, how many questions there are going to be. Plus, some of the questions might have multiple parts to them, and so I can't really answer that. But I will tell you that it is going to have a little bit of everything from chapters 1 through 5. So in that regard, let's kind of talk about what we've covered and what we've seen. So chapter 1 was all about data and sampling. So the important things to get from chapter 1 were all, the big thing is the terminology. You may remember that we defined all kinds of things there, like population versus sample and variable and data and parameter. And okay, so like know the terminology. You may remember on quiz 1, I gave you that question that said, here's something, tell me which of the following is the variable and which of the following is the parameter. And, so know those terms, know the different sampling types and how they're done and what they look like, so like the difference between, say, cluster versus stratified, like that's one that a lot of times people get confused. So know the different types of sampling designs, right? So that was a big part of it. But also in chapter 1, we talked about frequency and frequency tables and things like that. So definitely know how to interpret frequency tables in terms of relative frequency, cumulative relative frequency versus just plain old frequency, things like that. Okay, so chapter 1 was just setting the table, but I am going to be asking you questions on that. So like I said, expect some things like, you know, tell me what kind of sampling design this is, or, you know, what is the population in this study, or, you know, things like that. All right, so that was chapter 1. So then chapter 2 was, now we're actually doing stuff with those numbers. We're displaying those numbers and we're describing them. So the things that we did there, we had all the different kinds of graphs. So make sure you know how to do histograms, which are the same as like bar charts, right? Except bar charts are for specific values, histograms are for intervals, but those were the, you get the frequency is written vertically with the bars. Know your stem and leaf plots, right? So those are a fast way of collecting data, so you can look and see, oh, we've got a whole bunch of them that start with 20 and all that. So remember how those work is when you have a number, the last digit, the very last digit, that's your leaf, and the rest of it is your stem. And so what we'll do is we'll write the stem, and then we'll write a leaf for each number in our data that starts with that same stem, right? And so, and then we put the stems in numerical order. So we had stem and leaf plots, histograms. We also had box and whisker plots. So those were the ones where we had to find the 5 key points, the max and the min, Q1 and Q3, and the median. And then we draw the box using Q1 and Q3 with the median as a line in the middle. And then your max and min form your whiskers. Okay, so know how to do your box and whisker plots. So we had all the different kinds of graphs, but then we also started to describe the data. So that's where we used mean, median, mode, standard deviation. So definitely know how to determine mean, median, and mode from a set of data. Also know how to use your technology to do that. I'm not going to expect that you're not using technology, right? It's a take-home exam, basically, right? It's going to open up at class time. So it's going to open up at 3:30. You're going to go to the Canvas shell. You're going to click on exam 1. And at 3:30, you're going to be able to upload it and start working on it. But you're going to be at home. You're going to have your notes. You're going to have your calculator. You're going to have your computer. Like, I know this. So know how to use your technology to do those calculations. Okay, so that was what chapter 2 was all about, was now describing the data, was organizing it and all these charts and graphs, and then, you know, describing it. Central tendencies, so mean, median, and mode, and so on. All right, so that was chapter 2. So chapter 1 and 2 is just all about, here's data. Then we started talking about probability. So chapter 3 was about probability. So again, there was some terminology there, things like mutually exclusive, dependent versus independent, you know, all that kind of stuff. So we did have some terminology, but then it was basically calculate probabilities. And the big idea behind probabilities is it's always fractions. The values are always between 0 and 1. 0 means impossible. 1 means it's gonna happen, right? So yeah, the different probabilities, but it was always total number of outcomes on the bottom, outcomes we're interested in on top, right? So that's just in general how you do probabilities, but there's also then the, how do you do the very specific combinations. So some key things, remember the difference between and or. And is much more restrictive. And means you have to be part of both events or both groups, or means that you're one or the other. Okay, so there was and or. The conditional, remember what that means to be conditional. We're putting a restriction so that now our total number that was on the bottom is most likely smaller because we put a bit of a restriction on it. The number that goes on top, again, we're going to find that the way that we normally do. So know about conditional and all that. Also, know how to use our contingency tables to help us with that. Those were the ones where it was, okay, so we're going to go out. I think one of the examples we did, we asked people how they felt about global climate change. I think there was that homework problem. And so we were talking to people that were politically conservative, liberal, very conservative, very liberal, whatever. And so we had the grid of the different things. Those are really, really useful when it comes time to calculating probabilities because it helps you separate things out. So know how to use your contingency tables. So there are going to be questions on probabilities. I'm not going to assume a ton of knowledge about things. So the few things that I am going to expect that you know about. Coins. I expect you know about the probabilities of flipping a coin. I expect you know the probabilities of rolling a die, just a standard die. We won't even get into any kind of crazy D&D stuff, but just regular old six-sided die. And just a general idea of playing cards. But if I ask anything with a deck of cards, I'll give you a little bit more information. I'll remind you things like, remember there are 52 cards in a deck. There are 13 of each of the 4 suits, or so I'll make sure that you've got that information because I'm not testing you on your knowledge of playing cards. Okay, that's not what I want to test you on. I want to use playing cards maybe as a way of testing probabilities. So yeah, be able to calculate probabilities given various scenarios. Also, don't forget about the difference between with and without replacement, because that can matter a lot, especially if the sample is small or our population is small. All right. So that was chapter 3, was all about probabilities and all that. So basically just know the terminology, know how to do the calculations, and then the contingency tables. I guess the one other thing we did there, we talked about Venn diagrams and tree diagrams. I'm not as concerned about those. I definitely think you should know Venn diagrams. The tree diagrams, I find Venn diagrams much more useful. But remember the idea of Venn diagrams is we've got our A and our B as circles. If there's an overlap, people that are in both A and B have to be in the section between circles. All right, so that was chapter 3. Chapter 4 and 5, those were probability density functions, probability distribution functions. So those were broken down to discrete for chapter 4 and continuous for chapter 5. So the whole idea of PDFs, though, they're telling us probabilities for the different values of our variable, of our random variable. In terms of the discrete, we talked really about 3 different ones. I know the book goes into more, but I'm going to look at just the 3. There was the binomial. So binomial, geometric, and Poisson. Right? That's the one that's spelled like poison, but with the double S. So binomial, those are the ones where there are only 2 possible outcomes. I like to think of it as yes or no. Right? So there are only 2 possible responses, and we need to know the probability of one of the responses. So we call it the probability of success. But this is anytime you have something where you're asking a question or investigating something where there are only 2 choices, right? So things where this doesn't work: favorite baseball team, If I say, what's your favorite baseball team? That's not going to be binomial because there are more than two possible answers to that. I mean, really, there's only one possible answer. I know you'll all say the Seattle Mariners. At least you'll say that if you want a good grade. But yeah, okay, obviously there's lots of different options for that, right? As opposed to, do you like going to baseball games? You're either going to say yes or you're going to say no. I mean, I guess you might go, well, maybe no. We'll just go yes or no. All right, so binomial have to have two possibilities and then a probability of success. All right, and just so you know, the Lakers are not a baseball team, Bruno, so nice try. All right, you could have at least said either Dodgers or Angels, and then I would have, you know, I still would have mocked you, but for a different reason. Okay. All right, Braves, and I'll give you that. I liked the Braves back in the 90s when they had crazy pitching. Greg Maddux was maybe my favorite player at the time. Anyway, I digress. Okay, so in terms of binomial, be able to do the calculations, figure out what your probabilities are of getting a certain number of elements or, you know, an interval, but make use of your technology. Use the binomial PDF for one specific value, the binomial CDF for an interval. Watch the words. Excuse me. Watch the words. More than, at least, no greater than, fewer than, right? There's all kinds of different ways we say it, and all of them can lead to different numbers. So read it very carefully. Make sure you're getting the right values. So anyway, so that was the binomial. Geometric was, okay, we're going to be doing an event until it occurs. So I'm going to roll a die and I'm going to keep rolling until I get a 6. And the geometric gives us the probability of needing n number of rolls. Okay, so it's related to binomial where there's success or failure. But now we're not counting successes. We're looking at how long until we get success. So that was geometric. So again, be able to do your computations there. And then Poisson. And Poisson was a time related thing. How long do we have to wait until something happens? And so that's the scenario for that guy. So for all of those, and it's actually a blanket statement for all PDFs, know how to figure out means, know how to figure out standard deviations, know how to find the probabilities of the various types. Okay, but anyway, so chapter 4 were the discrete, and we looked at those 3 main distributions. Okay, so then chapter 5 was where we started looking at the continuous random variables, and there we looked at 2. Right. So first of all, just know that there are the 2 different the difference between continuous and discrete PDFs. The big difference for continuous now is that we're looking for area under the curve. The total area has to equal 1. And the area of any one specific event, or the probability of any one specific event is actually 0. It will not happen. But if we make a little bit of an interval around it, now we can calculate the probabilities. Okay, so those are the big differences. And we looked at 2 specific ones. We looked at uniform distribution. Think about that problem we did for homework, or the homework question earlier today. That's a really good example of all the different kinds of things that you can do for uniform. I'm actually really glad you guys asked about that one, because we were able to do like everything. All right, we did probabilities between interval, we did a probability greater than, we did some percentile stuff, we did there's a lot to, we did a conditional. So there's uniform, but that one's nice because areas are always rectangles. Oh my God, they're always rectangles. They're super easy. And then exponential, the nice thing about the exponential is that the formulas are known You do need calculus to do them, but the formulas are known, so they're pretty easy to do. Okay, so again, just like with the discrete, for the continuous, know how to find the means, the standard deviations, and interpret them. Okay, so those were all the topics. So the kinds of questions you're going to get, again, look at the quizzes and the homeworks, and you're going to know it's going to feel like it's a lot of it is word problems, and it is. I mean, statistics is very much word problems. So some key things: read it carefully, figure out what you're being asked. If it has something to do with a distribution function, make sure you can recognize what the distribution function is, right? Because finding the mean is very different depending upon which one you're doing. So other than that, I don't know what to tell you about what's going to happen, but other than it's going to be stuff that you've seen. Nothing should be a total curveball, right? There will be some questions that make you think. There always will be. But it's not like I'm going to put some really random, suppose we create some weird density function that's given by I'm not going to do that to you, right? This is more a, can you actually do what we've talked about? All right, so we still have just about 10 minutes left. So I'm going to open it up to you guys. What kind of questions do you have for me regarding this? Are there topics you want to look at and talk about? And I will also put this out here that don't feel like I'm pressuring you to come up with questions. If you have them, great. If you don't, that's fine too. All right, but I just want to use this time to address the things that you guys need, because you know that better than I do. So anything you guys want to talk about? Any questions you've got?
I had a quick question about exponential density functions. What do we use as like a keyword for deciphering whether it's an exponential function or not?
It'll tell you. For an exponential, yeah, that'll be the kind of thing where it'll say such and such follows an exponential distribution function, or it'll say something like that. You'll start seeing that a lot, actually, even in a lot of the homeworks. They'll say, this is uniformly distributed or follows a normal distribution. So on this exam, if you run into anything that requires exponential, it will tell you that, this variable follows an exponential distribution.
All right, got it. Yeah, thank you.
Okay, yeah, you're welcome. Good question. What else you got for me?
Can I ask a question about something homework related?
Sure.
Well, it's on, it is, hold on, let me go to it real quick. It is question 5 on chapter 4, discrete probability and binomial distribution.
Okay, let me go ahead and pull that up real fast. Okay.
And I think because I got the first few parts, it's just the last two that I'm having a hard time with C and D, where it says at least 24 of them survive their first year.
Okay. So mine's a little bit different, but let me go ahead and share mine so everybody can see. But it has the same wording, I think, right, Bruno, where you're saying at least 24 for yours. Mine says at least 21 and so on. Right. So is this going to be good enough for you?
Yeah, this is going to be good enough.
Okay, cool. So let's just look at this. So it says 61% of all Americans are homeowners. If 35 Americans are randomly selected, find the probability that exactly 23 of them are homeowners, at most 23 are homeowners, at least 21 are homeowners, and between 18 and 26, including 18 and 26, are homeowners. Okay, so let's start with this. Excuse me. How do we know that this is binomial? because it is binomial. But how do you know that it's binomial?
Well, it depends on the response on whether they are a homeowner or not a homeowner.
Yeah, that's exactly it. It's like if we go and what's the question we're asking? We're going to everybody and we're saying, hey, Bruno, are you a homeowner? Hey, Carolina, are you a homeowner? Hey, Carson, are you a homeowner? And you have one of two possible answers. You either say, yep, or no. Right? You either do own a home or you don't. So there are only two options. So it's definitely binomial. All right, so since it's binomial, we need to know two things. We need to know the number of our sample, which they tell us right here, right? They say 35 Americans are going to be randomly selected. So that's going to be our N. And then we need a probability of success.
That's going to be the 61%, right?
Okay, so this is going to be 61%. So we're going to use P as 0.61. And so a success means that you answered yes to that question, right? That you are a homeowner. So I go to you, I say, hey, Bruno, are you a homeowner? There's a 61% chance that you say yes. And then I'm successful, yay. All right, so are we cool with the interpretation of this, like as a whole?
Yeah, I'm good with the interpretation. Is more or less like the reading that comes after it, like at least, at most. Like totally. I was able to figure out at most, but I couldn't really figure out at least in the last, well, pretty much the last two. That's where.
Okay, so the exactly 23, that should be pretty easy, right? If it says exactly, we know that that's going to be x equals 23. I'm going to go to a whiteboard so I can write this stuff down in a probability kind of format. Okay, so the first one was exactly 23. So exactly 23. So this is going to be the probability that x equals 23. So this is one where we're going to want to use the command Binomial Pdf. You're going to put in 35, 0.61, and then 23. Most likely, that's the order that you put them in. If you've got like that TI-84 or whatever, it will actually tell you to plug in stuff. But so this is the N, P, and X. All right, so that was exactly. So then the second one was at most 23. Okay, so let's think about what that could be allowed, what we could allow. It could be 0. It could be 10. It could be any number under 23. Is 23 okay in this case? If we say at most?
No, if it's at most, wouldn't that imply? At most 23.
Yeah.
Oh.
It actually turns out that that does include 23. So whenever you see at most, just a little this at most, or at least does the same thing. This includes. All right, so if you ever see, if it says at most, that's going to be a less than or equal. If it says at least, that's a greater than or equal.
I see.
Okay, so and in fact, so the third part, C said at least 21. That's going to be a probability that X is greater than or equal to 21. So for these, we're going to use CDFs. We're going to use the cumulative distribution function because we've got more than just one value. And let me write out D as well. When it said between 18 and 16, including 18 and 16, or sorry, 26. That's going to be this one with the or equals. And so for all three of these are going to require some version of binomial CDF. And again, it depends on your calculator and what the specific command is, because some of them do CDFs from 0 up to and including that number. So like for part B, it would be a CDF of 23. But others, you can specify lower and upper bounds. But for all of them, CDFs, these always include the endpoint. So if it's just a less than or just a greater than, you need to make sure you take away the binomial PDF for that number. Let me show you real quick what the phrase would be, or what some phrases would be that would lead to an inequality that's just greater than or less than. So if you had more than, that's a greater, right? As also less than. So those are pretty obvious, I think, when you see more than and less than. But also you could have obviously fewer. Let's see, I'm trying to think of some other phrasing. Oh, how about this one? What if I said no more than 10? What would that one be?
No more than 10, so wouldn't that be less than or equal to 10?
Good, that would be less than or equal. I can't have more than 10. I can have 10, but I can't have more than 10. So like that's another phrase you'll see. But the at most or at least, those are definitely inclusive. Those are or equals.
And what would the command look like for the, because I know what it looks like for the at most, but for the at least, is that one the same as the at most, or do I have to tinker with it a little bit?
Okay, so again, it's going to depend on your calculator. But what kind of calculator do you have, by the way, Bruno?
I have a TI-84 Plus.
Okay, cool. Well, then here's what I'm going to do. Let me pull up my emulator, and we'll actually do it. Give me 1 second here. Got to pull it back up. Okay. So let me just go ahead and clear all this stuff from where it was before. So we're going to go into distribution. So second distribution. We're doing a binomial. Let's go find it. So we're going to do binomial CDF. Okay, so this one, we're going to start with the trials. So for me, it was 35. The P was 0.61. Okay, so then this one says X value. So this is going to be the type that does the from 0 up to and including that number. So like for that second one where we were going to do at most 23, this is what it would look like. So we're going to do binomial CDF, 35 trials, 61% success rate, and at most 23. All right, so now this one, we're gonna have to get a little creative for the at least 21. So let me go back to the whiteboard. So let me just erase over here. And let's think about how this is playing out. So I'm gonna draw just a real number line. So just think about this. So over here is 0. Up here is 35. So they're all my possible responses. And so somewhere in here is 21. And then there's also a 20 and so on. 23, all the way out here to 35. Now, the thing about CDF is CDF goes from 0 up to a number. So let's think about 0, 1, 2, 3, all the way up to 20. Because those are the ones I want to get rid of, right? Those are basically the ones I don't want. Well, this first group, this would be a binomial CDF of 20. It's going to add up 0 plus 1 plus 2 all the way up to 20. All right, well, I don't want those. I want the rest of them. So what's the trick to getting the rest of them?
Wouldn't we need to subtract the binom CDF 20 from the rest of that, or?
Well, we're going to subtract it from the total. And what's our total probability?
Our total probability, it's 61, right? Or
that's the probability of any one event happening. But what's the probability, total probability of one of these events occurring? That I get 0 responses, or I get 1 response, or I get all the way up to 35. Well, the total is always 1 for a probability density function. So to get this one, we're going to do 1 minus binomial CDF of 20, because this is the complement. Remember, complements are the other possible outcomes. And we know that if you add up the probabilities of complements, they equal 1. So with your calculator, if you've got a TI-84, if it looks like my emulator, what we're going to have to do is 1 minus the binomial CDF for 20. So let's look at the 18 through 26. So same picture, 35, 0. Somewhere on here is 18, and then somewhere up here is 26. So this time, I want just 18, 19, 20, up through 26. So if I did the binomial CDF of 26, that's going to give me all of these, right? Because we're going to go 0 up to 26. But that's way more than I want. I want to get rid of 0, 1, 2, 3, all the way up to this last guy, which is 17. So I'm going to subtract, because I want to get rid of them. And what number am I going to put here in my binomial CDF to get rid of all the blue ones?
17.
17, because I want to get rid of all the ones 17 and under. So I'm a real visual guy, so I always draw these pictures because it really helps me kind of see what's going on, right? Think about what we did here with the 1 minus. The entirety, this entire thing has probability 1. I'm going to get one of those results. One of those is going to happen. So I need to take away these guys. Well, that was my 1 minus the binomial of CDF of 20. So with your calculator, that's how you're going to have to go about it. Some of you will have calculators that actually let you do both endpoints. Like I think my TI-89 does that. And you're a little bit luckier in that regard. But yeah, that's how you're going to have to do it with yours. So hopefully that's making a little bit more sense with what needs to happen there. All right, well, I'm sorry, what was that?
No, I said it makes sense now.
Okay, good. All right, well, I see that we're actually out of time. So I'm gonna go ahead and stop the recording. But again, don't forget tonight, get your homeworks, assignment stuff in by midnight. And project number 1 also needs to be uploaded by midnight tonight. And then the exam, show up to not class. Don't come to class. If you come to the class, nobody's gonna be there. Go to the Canvas shell and download the exam. I'll send out a message Thursday morning just to remind everybody, but don't forget to do that. All right, so with that, have an awesome couple days. I guess I actually won't see anybody for a week, but good luck on your exam, and I will see you next class.